All right. Last thing we're going to take an opportunity to cover tonight and just kind of wrap things up and get things finished is the concept of Le Chatelier's principle. And equilibrium can be disturbed in a variety of different ways. This results in either the forward reaction speeding up or the reverse reaction speeding up in order to reestablish equilibrium. Essentially, we call these shifts, okay? And a system at equilibrium, which is disturbed, is going to generate either more reactants or more products in order to reestablish chemical equilibrium, okay? So when a system's in equilibrium, obviously the forward rate and reverse rate are the same. Well, we can do stuff to the system at equilibrium to cause it to not be in equilibrium anymore. And what ends up happening is that the system responds in a way in order to reestablish equilibrium by either shifting towards the left, creating more products, creating more reactants, or shifting towards the right, creating more products. So what we're going to do is we're going to take a look at each of these shifts and try to get a better understanding of how chemical equilibrium changes when a system is disturbed. Okay? So systems can be predicted, or shifts in equilibrium rather, can be predicted when a system at equilibrium is stressed. We can either have one of a variety of different factors that plays a role in this. One of these is an addition of a chemical or the removal of a chemical. Another one would be a change in pressure or a change in temperature. So we're going to look at each individual one of these to get a better understanding of how these particular changes causes shifts in equilibrium, okay? The addition of a reactant causes the system to respond by making more product in order to reestablish equilibrium, okay? So I don't know how else to describe it. If you add in more product, the system's going to respond in order to, when you add in more reactant, the system's going to respond to make more product in order to reestablish equilibrium. When you add more product, the system's going to respond to make more reactant in order to reestablish equilibrium. So kind of think it like balancing. If I get more reactant, well, in order to make equilibrium occur, I've got to end up making more product as a result of that. When you add product to the system responds by making more reactant. So by adding something, we end up causing the opposite thing to gain in order to reestablish equilibrium. Now, the opposite is true if we remove something. If we remove a reactant, the system's going to respond by making more of that reactant in order to reestablish equilibrium. And the opposite can be true if we remove a product. When we remove a product, the system's going to respond by making more product in order to reestablish equilibrium. So these are all pretty straightforward. We just have to think about whether we're adding or removing something and how the system's going to respond in order to reestablish equilibrium. So that's that's two of the three ways in order to do this. Okay, if we're adding in pressure, okay, what we want to take a look at is the side of the chemical reaction that has fewer moles of gas. So if we add pressure, it favors the side with fewer moles of gas. How do we know which side has fewer moles of gas? Well, what we're going to do is we're going to pay attention to the coefficients of the equation. The coefficients of the balanced chemical equation tell us how many relative moles of gas are in each side. So for example, if I had one side that had 2 NO2, well, that tells us that that side has 2 moles of gas that are associated with it. Like I said, we'll spend a little more time going through and looking at these when we go through and do some practice problems, but I just want to establish kind of a baseline here. And when we decrease the pressure, the reaction is going to shift to favor the side with more moles of gas. All right? So if we're looking at pressure, we need to look at the side of the chemical reaction that has either fewer moles of gas or more moles of gas, and then make sure we make adjustments accordingly. Okay, so increasing temperature favors products and an endothermic reaction, and reactants in an exothermic reaction. And decreasing temperature favors products in an endothermic reaction and products in an exothermic. This is a bit complicated, okay? I prefer to think of heat in regards to temperature. So here's how I would go through and do this. The first thing I would do is to determine if the reaction is endothermic or exothermic, and that can be based off of a wide variety of different factors here. But essentially, you're going to go through the process and figure out, is the reaction endothermic or exothermic? And that can be based on the change in energy that's present. It may tell you that it's endo or exothermic. It may just put heat on one side or the other. You can, based off of information in the problem, determine whether the reaction is endo or exothermic. Then you treat heat like an amount. So if I were to increase the temperature, then the heat would go up. And if I were to decrease the temperature, then the heat would go down. And then we treat it like a reactant or product in regards to how we work to reestablish chemical equilibrium. All right? So like I said, I know I've thrown a lot at you in regards to Le Chatelier's principle. It's really one of those things that's best seen as we go through and maybe run some practice with it, which is exactly what we're going to do here in just a moment. All right, so what we're going to do here is we're going to utilize this balanced chemical equation here, and we are going to determine whether the changes that we make to this are either going to shift equilibrium to the left, to the right, or potentially make no changes at all. So let's go through and take a look at this and analyze it. The first one says to add N2O4. So what we're doing here is we're adding a product to our reaction. Well, in order to reestablish chemical equilibrium, the reaction is going to shift to the left in order to reestablish that. Okay. Next one here. Remove NO. So NO is going to go down. We're removing a reactant. So in order to reestablish equilibrium, we're going to shift left to make more reactant. So that's all I really want to know. Am I going to shift left, shift right? You can say more reactant, more product. Either of those are perfectly acceptable as long as you're in some way, shape, or form indicating changes or chemical changes in the reaction in order to reach equilibrium. Decrease in temperature. So notice that your delta H, or your change in energy here, is negative. Remember that a negative change in energy is an exothermic process, which means that it is releasing energy. So what we're going to do here is we're going to consider heat to be a product. So in an exothermic reaction, heat's going to be a product, and in an endothermic reaction, it's going to behave as a reactant. So as a result of this, heat is on our right-hand side, decrease in temperature. We treat heat just like a reactant or product. So as a result of this reaction, heat is going to go down. So a product is decreasing. We shift to the right in order to reestablish equilibrium. Okay? The one thing here that isn't included, or something that we haven't really talked a whole lot about, is this addition of N2. N2 is not in the reaction, so there is no shift, okay, or no changes when chemical equilibrium is established there. All right? Let's do one more set of practice problems. So by removing a product, we are going to shift equilibrium to the right in order to, well, reestablish chemical equilibrium. If we add in some CS2, so in this case now we are adding in, a product. When we add a product, we shift to make more reactant in order to reestablish equilibrium. Again, it's just a set of rules that we need to make sure that we go through and memorize and practice with. In addition to that, we're going to increase the temperature. Now, I've gone ahead and told you that heat is a reactant in this reaction. In some instances, I might tell you that this is an endothermic process, so heat would go on the left side. I might tell you that the change in energy is positive. That would tell you that it is an endothermic process and heat goes on the left side. But again, we're going to increase the temperature. We treat heat like a reactant or product, so when we increase the amount of reactant, we're going to shift to make more product as a result of that. And then lastly, it talks about a decrease in pressure. Remember that a decrease in pressure favors the side with more moles. So this would be a good time to establish what I mean by more moles. Take a look at the coefficients of your balanced chemical equation here. So CH4 has a coefficient of 1, and H2S has a coefficient of 2. So that tells us that we have 3 moles of gas on the left side, and 1 plus 4 is 5 on the right side of my equation. So what that tells me is that it's going to favor the side with more moles, which favors the side with 5. So we're going to shift right in order to reestablish equilibrium. So again, ladies and gentlemen, it is just all about practice and ensuring that you are in just a good state to be able to understand how all of these shifts impact the concept of chemical equilibrium. They're easy points per se, as long as you know the rules, but they can be easy to miss if you do not understand the fundamental rules and concepts related to Le Chatelier's principle. So just last couple things before we are done. There are a couple of things that we can add or change that do not cause a shift in chemical equilibrium. One of those is by the addition of a catalyst. A catalyst will speed up the rate of a chemical reaction, but will not have an impact on the equilibrium position. So if you do see the addition of a catalyst as part of this, then it does not have an impact on chemical equilibrium. In addition to that, it is the addition of an inert substance. That is a substance that is considered non-reactive, one that does not play a role in the chemical reaction itself. So if you see the addition of a chemical that is not part of the chemical reaction, then it is not part of the equation, and we do not need to worry about its shift or impact on chemical equilibrium. So addition of an inert substance, one that's not part of the reaction, and addition of a catalyst, something you do not worry about in regards to equilibrium. That's all I've got for chapter number 9. I know it seems like it's been quite a quick. I did go through it a little bit quickly, but I wanted to make sure to try to keep this as short as possible. I know I say as short as possible. It is well over an hour, but I appreciate your time. Thank you for watching, and if you have any comments or anything, just make sure that you let me know. Have a great day, everybody, and we will see you soon.